Okay, so a lot of the same stuff going on, but this time we have that negative out in front. That negative in front. So we think back to what the negatives in front do, and that flipped it across the x-axis. So instead of going up, so there's my original basic shape. So original basic shape. Was that? My flipped shape. And I'm not very good at these things. Yeah, okay. I'm not, I had to stop and think about it. So before I flip it, it's going through the point 0, 1. When I flip it across the x-axis, instead of going through 0, 1, it's going to go through 0, -1. That right there, it's 1 unit above the x-axis. When I flip it, it's going to be 1 unit below the x-axis, and that's a bad graph. And it's going to look something like that. So there's my flipped shape. Everything else is going to be the same as before. The -2 inside, that's going to send me right 2 units. And the +4 on the end. On the end, that's going to send me up 4. Okay, so trying to draw this shape. So it starts right there. When we flip it, and I'm going to draw the flipped graph in yellow. This is not my final answer. So there's my flipped graph. Now let's move this guy right 2 units. 1, 2, up 4. 1, 2, 3, 4. And so that's what, and then my asymptote, move that asymptote too. We want to go up 4 on that asymptote. So moving that asymptote up 1 more unit makes my thing, my asymptote right there. So I move my asymptote, and I should have graphed my point first. But moving this point first, right 2, up 4, puts that final point right there. And then draw my same basic shape. And there's my graph. It's not a very good graph, but it's good enough. And there's my graph. Then the same question, same information. Domain, the domain on all of these guys is going to be -infinity to infinity every single time. And this is the answer. This was only the flipped graph. Yellow was flipped only. Here's the answer. My range, low to high. Well, low, it's going down forever now. High, we move that x-axis up 4 units, 1, 2, 3, 4. So my asymptote was at y = 4. So my range, 0 to 4, and my horizontal asymptote is also y = 4. For some reason I wrote an x, even though I said y. Y = 4. So it's still doing the same basic stuff. But each time what we're moving around is that 0, 1 point, doing what we need to do to it, and then moving the horizontal asymptote. But domain is always going to be -infinity to infinity. The range is either going to be number to infinity or -infinity to a number, and then the horizontal asymptote has a tendency to move around. Okay, so those are the basic guys. Now we're going to switch to a very, very specialized exponential function. It's not a basic exponential function. It's not a to the x. So we would not have these same basic facts. A very specialized exponential function. This guy. Consider f of x equal 1 plus 1 divided by x, or 1 over x raised to the x. And you do not have to memorize this at all. Please don't memorize it. If we make a table of values for increasingly large values of x, so if we plug in 100, you're going to get this number back. 1,000, you're going to get that. 10,000, so on. And notice as we keep getting bigger and bigger and bigger, and let's cut this off right here. Notice we get less of an increase each time. Even though we've multiplied our x coordinate by 10, our f of x value or our y value only went up. They agreed on the first 2 digits, and on the third digit, it went from 0 to 1. Then we multiply by another 10, and now we get agreement on the 2, the 7, and the 1, and then they finally change. Multiply by another 10, so the 100,000, we get agreement on the 2, the 7, the 1, the 8. Multiply by another 10, we get 1,000,000. We agree on the 2, the 7, the 1, the 8, and the 2. Multiply by another 10, we agree on the 2, the 7, the 1, the 8, the 2, and the 8. That as we get bigger and bigger and bigger, as this side goes further and further and further towards infinity, this number isn't getting that much bigger. We keep getting more and more agreement on each and one of those numbers. And what this number approaches, or this approaches a fixed number that mathematicians have called E. And that's what it all says down here. We note as the value of x gets bigger and bigger, the value of f of x does not continue to grow, does not continue to grow without bound. We say that f of x is approaching a fixed number, and we call this fixed number E. E is a number. E is a number. Like pi, E is irrational, meaning its decimal expression continues forever without repetition. The number E is approximately equal to 2.718. It is important to remember that E is a number. Just like pi, if someone asks you what pi is, you're probably going to spit out 3.14. That's not really pi, that's an approximation of pi. And the same thing here, E is approximately equal to 2.718, but the number really goes on and on forever. Now your calculator does know E. Again, this is for a TI-83-84. To find E on a TI-83-84, and there's my very old TI-83. We'll clear that out. Press second and the division symbol. And notice that gives me the letter E, but really is the number E, and press enter, and there it tells you what the value of E is. So it can absolutely give you the value of E. This will give you the approximate value of E. To get E and the symbol for an exponent, if you have an older calculator, or E with a little box that you can fill in the exponent. If you need to raise E to an exponent, it's second and ln. We'll talk about what ln means in the next section. But I press second and that ln button, and I get E with an older calculator, the little caret symbol for an exponent. If you have a newer calculator, it's just waiting there with a little box for you to fill in the exponent. So doing this first problem here, approximate E to the 4.1 using a calculator. So let's clear that old stuff out, clear everything. If I need E to an exponent, it's second ln. And then you just put in the exponent, 4.1. Best to go ahead and end the exponent if you're using an old calculator. If you have a newer calculator, you can just hit enter. And you hit enter. And there's my answer. So we'd write 6.340. And then however many decimal places my math lab says to use. So I'll call that a 3. And so there's E to that. Graph E to the x. Now I didn't say this before, but we could have checked these guys on a calculator, because your calculator can graph these things. So y, let's clear that out. E to an exponent. So second natural log gives me E to an exponent. Then I put in x. And It works most of the time, so let's give it a try. The standard window, zoom 6. I'm just going to think about it a while, and there's my graph, but notice it has that same basic shape. Now let's do a little bit better job. We clearly don't need all this blank space down here, and we already, so let's get rid of that blank space. Let's hit window, and instead of from -10 to 10 on the y-axis, just so I can see the axis, let's go y. Let's go -1, say to 21, or let's make it symmetric, -2 to say 22, and I'll count that by 2's and graph that. And it's not important how I choose those numbers, but the point here, notice I get that same basic shape. And again, it's going through that point 0, 1. If I do a trace and tell it to go to 0, which it did automatically, 0, 1. And so once again, I get that same basic shape like that. That all basic exponential functions have that same basic shape. So the important thing to remember here is that E is a number. It's approximately equal to 2.718. It's a number. Okay, one more time, use transformations of the graph e to the x. Use the graph to determine domain, range, and asymptote. So same idea. The minus in front flips it across the x-axis. The -5 in the exponent. So that's horizontal, goes opposite to what you'd expect, right 5. So remember my basic shape, what some books, some videos call parent shape, was that guy. So we're just going to do what we need to do. So we're going to flip it. Flipped. There's my flipped shape. Just like before. Originally, it's going up. Originally, that important point, 0, 1, was 1 unit above the x-axis. Now that important point is 1 unit below the x-axis. And then right 5. 1, 2, 3, 4, 5. And so there's that new important point. And there's, not a pretty picture, but a good enough picture. Not an artist. My grandmother was an artist. Oh, that's even worse. My grandmother was an artist. Instead of telling a story, I should be concentrating graphing it. We'll see if I can do both. There. I missed that point a little bit. When you miss the point, just make the point bigger. Well, my grandmother was an artist, but fortunately, my father was adopted, so I was very fortunate for him, but unfortunately no genetics, and no artist genetics. But there's my graph. Now notice here I didn't mess around with the asymptote because the asymptote only changes when I move up and down. Since my asymptote in the original graph is the x-axis, that asymptote can only change when I move up and down. It never changes when I move left to right. So I didn't have to change my asymptote. Domain, always -infinity to infinity. Range, low to high. Well, low, it's going down forever, and then it's going up to almost y equals 0. So -infinity to 0. And horizontal asymptote, y equals 0. And that's good for this video. We'll do some applications on the next video.